Welcome to Lesson 8-2, Composite Argument and Linear Combination Properties. The objective of this lesson is to derive a composite argument property expressing cosine A minus B in terms of cosines and sines of A and B, and use it to express a linear combination of cosine and sine as a single cosine with a phase displacement. So we're going to start this lesson with the linear combination property. When you say linear combination property, you can actually derive a mixture or a combination of two sinusoidal functions, say, as we have already introduced you a while ago or in the previous video. We graph y is equal to 3 cosine theta plus 4 sine theta. Now these two functions, these two sinusoidal functions, 3 cosine theta and 4 sine theta, have their own characteristic graphs, such that looking at this, we have this dashed line here with the smaller dashes as the 4 sine theta. And we also have the cosine theta, which is the one in long dashes. So when we combine these two sinusoids, we create a mixture of the sinusoids with the graph whose amplitudes are greater or are more than, when they have the individual phases. Looking at the combined sinusoidal graph, looking at this, we still have the same sinusoidal axis, but the amplitude is greater. So the linear combination property states that we could combine two sinusoidal functions together with different phases. And also, by way of composite argument property, which involves cosine of a certain function subtracted to another function in terms of cosine and sine of A and B, then we can use it to express a linear combination. So without further ado, let's move on further to this lesson. So with your grapher with you, we will prove that y is equal to a cosine theta minus d will equal a certain mixture of the sinusoidal functions. Now, taking this original graph here, in your grapher will tell you that the amplitude will be 5. Okay? And that the displacement is somehow, in terms of degrees, would be 53.1301. So that's the phase displacement of this function. Okay? Which is somewhere here. This is the phase displacement. Okay. Now D is the angle in standard position with u is equal to 3. Now take note, we have 3 cosine of theta plus 4 sine of theta. That's our y. U is equal to 3. That's the coefficient of the cosine, right? And v is equal to 4, which is the coefficient of the sine. Okay? So you can see this relationship that once we derive the composite argument property mentioned in the objective, we can prove that the amplitude is the length of the hypotenuse of the reference triangle for angle D. Okay? Now you can find the length A, which A is the amplitude, by getting the Pythagorean relationship from the two coefficients A and B. Okay? And that means that C, let's call it C, the hypotenuse. So C square, using the Pythagorean relationship, because we have defined a right triangle, C square is equal to A square plus B square. So our C here would be equal to the square root of 3 square plus 4 square, and that will give us a value of 5. Okay, so in the combination property, or which combines the two sinusoids, which is defined by this defines a linear combination property. And then introducing the composite argument property, which is defined by this expression. Okay, now this defines the composite argument property, and writing the composite argument property taken from this linear combination property gives us y is equal to a, which is the amplitude, cosine of theta minus the displacement d. And that means that our equation using the composite argument property would be 5 cosine of theta minus 53.1301 degrees, and this is just equal to this expression. Okay, but how did we get 53.1301? Now that remains a mystery. So after getting the value of our amplitude, which is actually a relationship between the two coefficients a and b, which are for u and for v. For a, that would be equivalent to u, and for b, that would be equivalent to v also, which is the coefficient of the sine, the coefficient of the cosine. So getting the Pythagorean relationship, our c is equal to 5. Now how do we find this d here? Okay, take note that if we take the arctan, so let's say tangent of d is equal to 4 over 3, right? So getting the arctan of this ratio, our calculator will give us, let's use it, we have 4 divided by 3 equals inverse tangent, we use degree here, so 53.1301 degrees. Okay, this is 15.1301, 53.1301 degrees. And then what's next? Well, for arctan, the inverse tangent, or the arctangent, so to speak, terminates from for the main, or for the principal branch of the arctangent. The arctangent terminates or is being considered for quadrants 1 and 4. 1 and 4, or no, 1 and let's go back to that. Okay, so going back to the lessons, the tangent, the inverse tangent terminates from 1, 2, and 4. Okay, so we will consider the principal branch 1 and 4 here. But in this case, the general solution for D should be equal to 53.1301. Okay, as per the general solution formula for arctangent, plus 180 degrees n. Okay, but we only want the first quadrant here, so we have to set n is equal to 0 so that D terminates in quadrant 1. It doesn't have any coterminals. Therefore, we found D, which is the phase displacement, and also the A, which is 5. So we could now find an equation fit using the composite argument property. And we did this by writing y is equal to 5 cosine theta minus 53.1301 degrees. Okay? So let us do an example. This is the first example in your book. Express y is equal to negative 8 cosine theta plus 3 sine theta as a single cosine with the phase displacement. Okay, so what is the general form? The general form is y is equal to a and then cosine is a single cosine, so we have cosine. Okay, a cosine of theta minus d. So what are the steps? First, we have to draw a triangle enunciating our sine and cosine. The coefficient of our cosine is negative 8, meaning that it should be here because our sine is positive. So we have coefficients. U is negative 8 and V is 3, meaning that the point being defined here is negative 8, 3. Okay, so where is negative 8, 3? It's on the second quadrant. So let's therefore draw a triangle on the second quadrant. Let's draw a right triangle. Okay, where U is negative 8 and V is 3. So in that case, now we have our triangle, and this is a right triangle. Okay, U is negative 8. So this is negative 8. The adjacent side is negative 8. And our V is 3. So how do we find our angle? Let's call the angle D. Okay, so our angle is D. It should be in standard position, so we should write the arrow counterclockwise. Okay, so this is D. Okay, what is the hypotenuse here, which reflects our A? This is our A, and A is the hypotenuse. So solving for A, let's create a bracket here. Solve for A in the box. Solving A in the box, we have A squared is equal to square root of, or the square of instead, the square of negative 8 plus the square of 3. So A will be equal to the square root of negative 8 squared plus 3 squared. And that will give us 64 plus 9. So that means that A is the square root of 73. Okay, how about the angle? So how do we find the angle? To find the angle theta, or d in this case, d is equal to the arctan of 3 over negative 8. Okay, and d will be equal to, what is d? We have 3 divided by 8 negative, that would be negative 0.375 inverse tangent, so that would be negative 20.556. And negative 20.556 is actually in the fourth quadrant, so we have to reflect it. That's negative 20.556. Let's approximate it to 56 degrees. Okay, and reflect it to the second quadrant, because our angle is located in the second quadrant. So D here would be equal to 180, or negative 20.56 degrees, plus 180, because the tangent are 120 degrees apart. Okay, so we will have, just add 180 here, 159.4439. Okay, so we have our A, we have our D. All we need to do is to write down these solutions so that we will have a composite argument expression for the solution. So our answer should be y is equal to, our A is square root of 73, and our phase displacement, so this is a cosine function. Okay, theta minus 159.4439. Okay, so that is the answer for example number 1.